Did you all get to look at the PowerPoint I put up there? It has all the definitions that are pertinent, like samples, randomness, and everything. I'm going to go through that today.
You need to remind you to talk about grad school.
Oh yes, thank you. And actually, I'm glad you said it right now. I just got done with a Zoom interview of a guy who's getting out of grad school. So I don't know if you guys get this from any other source, but graduate school is something almost nobody talks to you about here. Now, graduate school and other universities and stuff, they really tell students, if you're a good student, stuff like this, a graduate degree will advance your career a lot. And it opens doors. So I try to tell people this. Now, when I was an undergrad, I was going to get out, and I was thinking about going to work. At that time, I was doing solid state microelectronic physics. It was in electrical and computer engineering, but at that time VLSI was real big, and I was going to go, I thought about different places. But then one guy really said it best. He goes, you'll never meet anybody that regrets going to grad school. And I'm paraphrasing. But you'll meet a lot of people that regret they didn't go. And it's something at the undergraduate level, all you guys are, if I equate this to something my friend from MIT told me, if knowledge is likened to water, then the undergraduate career is like trying to get a drink from a fire hose. Most of it flies by. You don't retain much. You're always putting out fires. A lot of times it's not very enjoyable, trying to take care of everything without enough time to really appreciate different subjects. In graduate school, it's completely different. Unless you really overload yourself, you really learn everything at a very deep level, and you get a lot of advanced stuff. Not only that, you find out what you really like. When I started grad school, I was doing solid state physics and a lot of microelectronic stuff. I did plasma etching and things like this, but I found I really loved electromagnetics, and my PhD was in modeling really transient electromagnetics, the transient electric field signatures from charge perturbations related to lightning. Really, it was about nuclear weapons. But anyway, it was something completely different than I started with. But I really enjoyed that, and that's how I ended up studying all this stuff. And now I do radar. I still do some lightning work occasionally, and I do things related to electromagnetics, EMC. Also do a lot of stuff with genetic algorithms to figure out another optimization, what materials are made of. But it opens a lot of doors. And another thing is it's paid for. Basically, if you want to go to grad school and you're a good student, if you're a really good student over 3.5 and stuff, you probably can get a fellowship, a government fellowship for 3 years, no questions asked, and they'll give you about $30,000 to $40,000, I haven't checked lately, plus pay for tuition. That's a lot of money. As a graduate student, I never had any concern about finances. And this is back in 1980, 81. And with yourself, I encourage people to do this. Go look online at the National Science Foundation Graduate Fellowships, or just look up Graduate Research Fellowships at NSF, DOD. All my American students, with the exception of maybe one, I think two actually, were on fellowships that were either NASA fellowships, Dan Faircloth was on that, DOD fellowships, Brian Cottle and Michael Allgood were on DOD. This is 3 years of money, no questions asked at that rate. They were, let's see, who else do I have? Mark Adams upstairs, he went to Caltech with an NSF fellowship. He finished his PhD, and I helped him get that thing. I had, I'm trying to think how many people. Kevin Driscoll was a NASA fellowship. Jacobs was a DOD fellowships, I think. But the basic thing I'm trying to tell you is there's a lot of people that will support you getting a graduate, even if you don't have a super high GPA. If you're interested in something, you get a graduate research or graduate teaching fellowship. There is no downside to it. And have you guys heard this before from anybody or not?
Dr. Birch.
Tom Birch? Hunter Birch? Yeah, well, and I don't know why they don't talk about this more. Now, the truth is most places, like when I was at Penn State, students wanted to go to grad school because they knew that opened other doors. Most people, they were good. But it was by that time, everybody knew the whole deal that, you go to grad school, if it's just financial, your average salary goes up a fair amount. And not only that, just how many different things you can do. You can't teach at a university setting like this as a professor without a PhD. It's a terminal degree, they call it. You can't do a lot of things. If you go to national labs, you're not going to be, in terms of the scientific areas, not administration, you're not going to go to the top of the directorate or anything like that because if you don't have a PhD. And that's one of these things that it allows you to do whatever you want. A lot of people I know, and this may be your trajectory of your life. If a lot of people, what they do is they figure out, they want to make a lot of money, which is a dangerous thing. I just warn you about that. If you want money, and I talked to one kid about this some time ago, I'll never forget him. Very bright guy, but he wanted to make a lot of money. So he got out of here and with an undergraduate degree. He was about a 4.0. I don't know what firm he worked for, but he went to Wall Street because Wall Street pays a lot of money, like probably 50% more than he would have got as an engineer. And about 4 or 5 years later, something like that, he called me and he told me who he was. I'm there, what are you doing? He's on Wall Street working for this firm. I don't remember the name of it, making a lot of money. Well, congratulations. He says, no, I hate it. This is interesting. Well, why are you doing it? I want to go to grad school. Now, that far down the line, you got a wife a lot of times, kids. It's very hard to go and relocate and do grad school, even do it online and stuff. I have I've got two cousins that did something like that with U.S. Steel. They got their bachelor's degrees from Penn State, but their doctorates from Carnegie Mellon and in materials and metallurgy, all right? But really, U.S. Steel underwrote basically their PhD, so they were doing work that was really related to. So it's not that easy to get that kind of a deal. And just remember what I'm telling you. This is the one time in your life you've got the background, you can take the next logical step and go to grad school. You don't have to go here. It's nice to go places, I'll tell you that. I was going to go to Cornell, but they made me an offer. It was pretty good, and I stayed at Penn State to do my PhD. But the real thing is this, look around and look at the options. Now, some people, they want to get a degree in business. They figure it this way, or law, and I know people that have done both. And some medicine, believe it or not, they go undergraduate electrical and computer engineering, and they take some courses in biology or whatever they need to take MCATs, and they're accepted in med school. Medical doctors make a lot of money. So they become medical doctors. I've had that happen more than a few times. Other people go and they become lawyers, patent lawyers. You know what they are? They make a lot of money. But again, they're chasing money, and that's, so be it if that's what they want to do. Some people like law. And other people go into business and they get an MBA. Now you're in you got a pretty good background to go and work for companies where they want you to be a business administration guy, but you have to have a good understanding of the things. And you know what Apple Computer is, right? Well, years ago, Steve Jobs was removed as the head of Apple. He's a very abrasive person and with the board, but he really knows his stuff. It's like a good football coach or anything. Not a nice guy, but he can make the thing work better than anybody. So they got rid of him and they brought in a guy, I think of Pepsi, this CEO for Pepsi, and he basically had the idea, microchips, potato chips, it's all the same, we're just selling stuff, we got to package it right inside. He had no clue about vision and all the other things it takes. No engineering background. Company almost failed. They brought him back, they brought Steve Jobs back, and then Apple thrived, and then he died. Now they got Tim Cook, who is an Auburn graduate, believe it or not. You guys know who this is? He graduated industrial engineering. I don't know him personally, but I know who he is. And now he does have a fair background technology, so he knows what he's doing. Anyway, if you got questions about it, talk to me afterwards. Today what I want to do, and I think I already tuned you into this, Chapter 4 in sampling. We're going to be talking about stuff that I find very interesting because I hear polls all the time, and most of the time they don't qualify or explain what they're talking about, and they're usually extraordinarily inaccurate when you hear polls about anything. especially politics. That's the worst. But I get called about cars. I get called about, they want me to give my opinion on stuff, about everything. And it's probably because my name's out there. I just say, I have no opinion. I like anything that's free. Want to give me a car? All right, so now we're talking about sampling. This is chapter 4. If you want to, you can pull up that slide. So with sampling, the whole deal is this. You're going to have a population, and it's going to have n members. So capital N is the number of people in it. If you can get the PowerPoint up, it'll save you writing, and it's very well organized. It's Tom Denny's old PowerPoint thing. He did it very well. Now, out of this, we're going to take a sample. We're going to take n of these things, and n is going to be much, much less than capital N. So we're taking a smaller group of these things. Now we're going to do something, and we're going to define certain things here. And if you look at the PowerPoint, you got it up now?
I'm pulled
All
up.
right.
He's got it.
All right, you got it. All right, first, he's going to talk about, in this sample size here, we're going to have something that is the actual mean of the things. This is going to have a small x, and it's going to be 1 over n, and it's going to be a summation of the actual values xi from I equals 1 to n, and that's just the mean, actual mean of the samples you took. That is not a random variable. Y'all see that? Can you see it there? Now, there's another thing. This will be a capital X, and I think he does something like this. Now, the capital X is a random variable. So imagine this. We're sampling this, right? We're taking n of these things, but we don't know what n we're taking. We could take n anywhere. This is the actual sample itself that we're talking about. One single sample, we get the mean of it. But if we talk about the sample itself being a random variable, in other words, here's n of these, but it could be n of these, n of these, n of these, then they use a capital X here, and it'll be, that mean is going to be the summation of now the random variable x of I, where I equals 1 to n times 1 over n. And I think he has this in his book. Do you all see that, class? So he's saying that, all right, this has got some randomness in it. Now we're talking about, we're sampling these things. It means that that has randomness as well. And it's also limited by n. So now the next thing they do is they say, well, if we have samples, and there's a couple things I have to mention. If you're sampling something, there's a lot of theory about this. You can sample something, say you got 100 resistors, you can measure it, then you can throw it back in, juggle the thing up, and grab another resistor. That's sample and replace. Or you can sample something, measure it, and not replace it. Those are two possibilities. So usually we start with the simplest thing. We say, if the number of, and I'll call this first part, if capital N is much, much greater than n, all right, and I should say this is always the case, but here we're assuming it's much, much greater than n. Then when you look at the actual, and in his book, if you want to look at his book, this is in section 2, I believe. I'll tell you where I'm at. Yeah, this is the expected value. This is at the bottom of page 161. He doesn't even have this equation number. But if you take a look at the expected value, and this is important, of the actual value of the random variable that is the summation of random variables. It's the average value of the random variables. You follow me? Now this thing, if you just think about this logically, what this really amounts to is going to be a summation, and here, and it'll be 1 over n of this, and then it's going to be an I equals 1 to n, and then it's going to be another summation. Well, actually, let me do it this way. I'll just state this explicitly. And I think he does this in his book. He goes through and he shows you, because this really is the expected value of 1 over n of x of I equals 1 to n here. What it amounts to is really the expected value of a random variable in that sample, and that will be the true mean of the sample. I mean, of the actual population. And he has this at the bottom of page 161. If you write this out, this gets a little abstract. You could write this out. Remember, this is a random variable, all right? But in the limit, as you take a look at this and you go through the entire sample space, capital N, where these things, the average value of that is going to be the average value of the expected value of the random variable, x of I, the subset of that. Just go with me on this one. You're going to have to just deal with it. You can read through the book on this. It should make kind of sense to you if you're thinking that this is a random variable, so we can sample any n, small n components out of n. The average value of this right here, of the average, should be the true mean. That's what he's getting at. That's all he's saying. And it is. So after that, the next thing he's going to talk about is the sample variance. And I want to do that over there. Some of the theory here, if you actually do, like write a MATLAB code to simulate this, you'll see it real well. So now this is the sample the variance, but it's the variance of x bar. So remember this. It's the variance of this. It's the variance of the average value. Now this gets a little, you have to think about this. You know, in general, when we talk about variance, it's variance of a member of a population. You know, a population is going to have statistics. You'll have a variance and you'll have a mean value, right? Now we're talking about the variance of the mean value. So think of that as a separate function. Make sense? And this is again, this is a random variable. So if you take a look at this, well, variance itself, and he does this, of x bar hat. And if you look at that, well, that's going to be a summation. And I mean, from the definition of variance, I have to square that value, and then I've got to sum it, right? Overall possibilities. So this is the sum, and it's going to be another sum, or j equals 1 to n, of, and now you're going to get this kind of deal. You're going to get x of I times x of j multiplied together. And you got to have 1 over n squared out in front. Let me explain this part. The 1 over n, all right, is going to have to do with the number of samples. So anytime you have a variance of something, you're going to have to go ahead. And normally, when we talk about variance, what do? The normal way to get the variance of anything is actually an integral of, if it's x squared, f of x dx over the range from minus infinity to infinity. That would be in continuous time. Do you all follow? Or continuous space. If it was going to be something where you actually had a finite number, then it would be a summation here, and it would be of x squared, x of I squared, and then it's going to be times the density function, which would be I'll just call it f of xi, and this would be from I equals 1 to n. Well, here we're taking a number of samples. The average value would be 1 over n of each of these things, and when you do the math on this one, this is going to come out to be, I'll tell you where this is in the book. This is equation 4-3 in the book. But what it's going to come down to, remember I've got two indices, j and x, or j and I here. So when these two are the same, it's x squared. You all follow me? When they're different, then it's going to be, I think he does it this way. He has n over n squared, and the summation really of x of I squared, I equals 1 to n here. And that's actually, that'll give you the first part. Actually, it's this. I'll just erase that and I'll give it to you. This is 1 over n squared, and it's going to be times n times x bar squared, that's the actual mean, plus n squared, actual variance, and, I mean not variance, but the mean value squared, mean squared value, plus n squared minus n times x bar squared. It's that, and then it's minus, this is actually x squared bar, my bad, minus x bar squared. Let me just say this. In the book, he goes through this, and to get the variance of anything, you're going to have to take the value of the function, multiply it by itself, and square it, because these are random variables, and of the sample mean itself. We're trying to find the variance of the mean. This is getting the variance of the average. So you have to take the average value of each, which is here. I broke it up. You can actually put x of I here and put a 1 over n here, and 1 over n times the average value. But the thing about these is that because it is a running average, you have to break it into two sums. You got to take the sum of the first, you might say random sample, times the sum of the second square. When you do all the multiplication of these things, you're going to get this, and when you get this, it actually boils down to simply be this will cancel this, because you got an n squared here, and you end up with getting, after you do the math on this, you're going to get sigma squared over n. Now sigma, and this is important, sigma squared is the actual or true variance of the population. And so this should be the formula he has if you have a large number of sample, or you have n is large, tending to infinity, and you got a subset that's much, much less. And this is the variance of x bar hat. So this relates variance to actual standard deviation, the number in the samples. You all follow me on this? What equation is that, by the way, if you're looking in your book? Anybody?
4-5.
All right, so this is equation 4-5. Now, next, they talk about, that's for this case right here, the variance of x is going to be equal to sigma squared over n. Part 2 of this is going to be if now it's going to be a smaller set, n less than capital N, but we're going to not replace item sample. This is in your book, and some of this stuff he doesn't exactly nail down, but he says there may be a situation, of course, in which one may not wish to replace a sample or may be unable to replace it. Basically, it's destructive testing in solid state. If you actually have components where you're going to test the failure and you want to see where the threshold is, something like that, you can't replace them once you destroy them. Things of that nature. For example, if testing is done of a life test or if test that involves destroying an item, replacement is not possible. This is on page 163, right above equation 4-5. Or public opinion polls, one simply does not wish to question the same person twice. In such a situation, it's still possible to calculate the variance. This is equation 4-5. He doesn't prove it either. So this, the variance of, remember, this is the variance of the sample mean. It's not the variance of that small set n. It's real important to understand this. Remember, this is a summation and an average of a sample, a small n. This, if we actually looked at the statistics of it and got a probability density function, is going to have a variance and a mean. Do you all follow me? The actual mean of that is the true mean, but the variance of this is going to be equal to, as before, sigma squared over n, but then you get this, you're going to get n minus small n over n minus 1. And you'll have this in here. remember one thing, capital N is total population size, and small n is sample size. Okay? Sigma here is the true standard deviation. Now, an obvious question or a comment might be, well, if you know the standard deviation, why are you worried about the variance in the actual sample size variation? What you're trying to do is get a handle on how accurate it is. How accurate is going to meet the mean value of this thing. That's the reason. You're going to see a lot more theory come forth because the obvious question is, well, how do you know the variance? I mean, the actual variance. If you know the actual variance, why are we doing all this? All right, you're going to see the reasons for this in the coming sections. So let's go with, sometimes they can tell the variance. I mean, they may not know the actual value of sigma, but they know statistically its relationship to the mean. So when I say sigma, I'm talking about the standard deviation or sigma squared, the variance of the true sample. You're going to see some problems like this. So this is the other one, and this is equation 4-5, I believe, right? So the best way to, after I put these two things up here, because they're a little odd to get a handle on, we might as well go ahead and do the exercises and problems, and that's the way I usually do this. So now I'm going to go ahead and do I think that's all the theory I need to put forward. Well, I can talk about how accurate this, when we get a mean and a standard, how accurate the standard deviation, the variance actually is, and they put thresholds on. But what I want to do is the exercises. In the next section, 4-3, that's where we really start talking about the level of accuracy or confidence you can have in this. It's called a confidence interval. Have you all heard that term, confidence interval? It means different things to different people. Okay, so for exercise, can you give me the first one?
Yeah, this is from the PowerPoints.
No, here. Just use my book. I'm not worried about, I want to do the ones in this book. Tom may have some other ones in his notes.
All right, so you want to start with 4-2.1?
Yeah.
All
This
right.
is exercise, though.
Yes, exercise.
4-2.1.
All right, he's given an endless production line is turning out solid-state diodes, and every 100th diode is tested for reverse current and forward current at diode voltages of -1 and +1.
So I of -1, I of +1. This is reverse and forward bias. Go ahead.
And then if the random variable I of -1 has a true mean value of 10 to the -6 and a variance of 10 to the -12,
10 to the -6 and a variance, so it's variance of I minus squared equal what? 10 to the -12?
yes.
Okay.
How many diodes must be tested to obtain a sample mean whose standard deviation is 5% of the true mean?
All right, now he's testing 1 out of 100. You all follow me? Every 1 out of 100. So the variance, in general, the variance of the sample right here, the variance of the sample, would be equal to sigma squared over n squared, over n, pardon me, if we assume that that we aren't doing destructive testing. I mean, in other words, if we're pulling one out and then same sample size pulling out, but this is continuous. Do y'all follow me? Every 100 things. So it looks like n's infinite, capital N. Do you follow me, class?
So basically, if capital N is much larger than small n?
Yes, yes. And you're not, it's not something where you're replacing or you're destructively testing something, you're reducing capital N. All right, this thing keeps coming. It's every 100th of these gets tested. Now, what does it say about this? This is the sigma squared is a true variance, and n's the number we're looking for, and it's, so this variance is, what does it say, 5% or 2% of that?
5% of the true mean.
All right, hear me on this one. You got to be careful. So this is the variance right here by definition. We're trying to find n. We have this. We have sigma squared of that. Okay, he's given us this one. So we've got the actual variance of the current the reverse current. So now he says it's, how many percent? 5?
5%.
So that means it's 0.05 times the actual true mean of that. Remember, if this right here, if we take the mean, 0.05 times this value here, now we get the actual measure that he's saying. It's 5% of the true mean, right? But he's saying that the standard deviation would be that, right? Not the variance. So, or I mean, if it's, doesn't he say that?
No, he said whose standard deviation. Yeah, so standard deviation
If
is
they
5% of the true mean.
So what he's really saying, if this is equal to 0.05 times I of minus 1, I of minus 1 is just an average value here, then if I look at this equation, which is the variance of the average of the mean values of the sample, now you've got to square that. So I'm going to put this in here. So we have we really have n equal to, if you look at this, it's going to be equal to sigma squared over 0.05 times I minus 1 squared. So sigma squared he gives as 10 to the minus 12th, and it's times 0.05 times I to the minus 1 is minus 6, right? 10 to the minus 6. So here you can see, and I got to square this. When I go ahead and square this down here, I get 10 to the minus 12th. It cancels that 10 to the minus 12th. Do you all see that? So I end up with 0.05 squared. And I think that's 625, but you can correct me if I'm wrong. Is it? I'm sorry. That isn't right. So it's going to be, what is that? That's 10 to the 4th over 25. What is that value going to be? So it's going to be 400, I think, right? Isn't that right? Okay.
That's one of the answers.
The only thing I did here was 10 to the 4th is going to be 100 times 100. 100 by 25 is 4. 4 times 100 is 400. That's okay? Yeah.
I'm just curious, on this PowerPoint, you used the other equation for variance and got an answer of 28.
For this one, no. If he's
You copied the problem on the PowerPoint?
no, if he's replacing it, yeah. But this is without replacement, right? I mean, this is
It says without replacement, so yours is with replacement?
no. This is an ongoing problem. This should be an answer. It should be right. Is it?
There's another example. You're looking at the wrong one.
Okay.
Sorry.
All right. Y'all with?
Had the same value.
Do y'all follow me on this one? This is an ongoing process. You consider n, capital N, going to infinity. It doesn't stop.
Okay.
All right. Next, what does he ask for?
All right, so if the random variable I of 1 has a true mean value of 0.1 and
Hold it. This is for
I positive 1.
this is for forward bias, right?
Yes.
Okay. So the true mean of this one is what?
0.1.
0.
And then a variance of 0.0.
0.1. That's
Yeah,
it.
0.1 for the
Okay,
mean
and a
value.
variance of
0.0025.
And now we're just going to apply this again. We're going to find the number of samples we need. Y'all follow me? And remember, we're taking 1 out of 100. So it's going to happen continually, right? We're going to take this many as a sample, as this process is going out. We're going to start grabbing samples, and we're going to take so many out of this continual process. So the next one is we have the variance here. And this is going to be of I plus is equal to sigma squared over n. And they say, what percent?
He wants the standard deviation to be 2% of the true mean.
All right, so if the standard deviation is 2% of the true mean, we take that 0.02 times the actual true mean, and then we have to square it to use this formula. Does everybody understand why, class? You with me on this one? Because standard deviation has to be squared to get variance. All right, so that means it's 0, and this is the variance of the 0.02, and the true mean is
0.1.
times 0.1, and we got to square that, right? So what is that? That's 2 times 10 to the minus third squared. Isn't that right?
Yes.
And now we can get n here for this one is going to be equal to 2 times 10 to the minus third squared over sigma squared. And sigma for that one was, or I mean, this is 0.0025. Wait a second, that ain't right. That can't be right. What did we do wrong? This is right here. Is this, oh wait, I did it wrong. Sorry. It should be n would be equal to 0.0025 is that one. That should be on top. And then I divide that by 2 times 10 to the minus third squared. That makes sense. What is that? Is that 625? Or am I wrong? Pardon me? Is it, that's, I think, one of the answers.
That's one of the
Remember,
answers.
they're not sequential. 625. Okay. And what's the third part of that one?
If the larger of the two numbers found in part A and B is used for both tests, what will the standard deviation of the sample mean be for each test?
All right. It's going to be the same for the second test. That's the number of samples. Do you all follow me? Doesn't change. We have already used it. So now we use 625 for the first test. Got me on this, guys? All right, I'm going to come back here. So for the first test here, now I say I've got this would be the variance of I just put minus for reverse current, minus 1. And here it's going to be the sigma squared, which is 10 to the minus 12 over 625. They want the actual variance, is that right?
Yes. Well, do they want the standard deviation? What will the standard deviation of the sample mean be for each test?
All right, so you got to take the square root of this to get the standard deviation. And this would be the square root of variance of I minus 1. Can somebody give that to me? That's 10 to the minus 6 over, I'm not even sure what that is. About 10 to the minus 4?
4 times 10 to the minus 8.
Here? Square
If you-
root of
if you
10 to the
do-
minus 12?
If you do square root of 10
Okay,
minus 12
okay.
over 625, it's 4 times 10 to the negative 8, and that's one of the answers.
You all with me, class? And again, we're just plugging and chugging. There's nothing tricky about that, in my opinion. But you have to become familiar with this term. So statistically speaking, if they plotted the actual probability of a sample mean having values, like on the horizontal axis, that would be a probability of sample mean having value from anywhere from like 0.1 to whatever. Then what you'd get is a density function that would probably look Gaussian, but it depends on a lot of things, similar to Gaussian. Then, if you take a look at that, what we're talking about is the variance in that density function. It gets a little hairy thinking about this stuff, but I hope you can appreciate this. This has to do with the statistics of the mean. Okay? Now, is there another exercise?
There is 4-2.2.
Okay, let's do that one. This is the only real way I figure I can do this effectively. He does stuff on the PowerPoints, Tom has all that, and it's good, but until you see it applied, you're going to have questions. And this is the one I think where it's, we're going to talk about basically a limited sample set, N. We're going to have capital N that's got a limited value, and now we're selecting out, but we're not replacing. So think of it as destructive testing. All right, now for this one, go ahead.
Okay, so you have a population of 100 resistors.
This is an exercise 4-2.2.
Yes.
So we got capital N is 100.
Yes.
Now that's a small. This is getting small right now. That's the total number. Go ahead.
And then it's to be tested without replacement
Yeah.
to obtain a sample mean whose standard deviation is 2% of the true population mean.
All right. So here we want standard deviation.
It's just telling us the information. And then the first question is, how large must the sample size be if the true population mean is 100 ohms and the true standard deviation is 5 ohms?
And then or sigma of R is 5 ohms, right?
Yes.
Okay. I always tell people, go from the first formula you know. This is sample, but it's destructive testing, all right? So that means we default to the other formula. This variance is going to start with sigma squared over n, and then you put capital N minus small n over capital N minus 1. All right, now that's the variance. They give us standard deviation, right? They want the standard deviation to be within something, right?
Within 2% of the true population mean.
All right, so then I'm going to set that equal to, since it's standard deviation, I got to square it so I can get the variance of the true population. So that's going to be equal to 0.02%, right?
Yes.
Of the actual true mean, right? And
Yes.
I should put R here, but I'm not, and I have to square it. With me? Now we put the variables in because we're looking for small n. Just take a good look at this. All right, so here, I can do this. I can say, well, what is this over here? This is really 0.02 times 100, right? Squared, or really, that's what? That's 2 squared, that's 4, isn't it, class? If I take 0.02 times 100, I get 2, I square it, I get 4. So I have 4 there. Now let me see what I can do with this. So now I have sigma squared, which is going to be 25, because that's sigma. So I got to square it, I get 25 over n. Here, capital N is 100 minus small n. N minus 1 is going to be 99, if you look at this. And again, the only thing I'm doing is replacing these symbols with the actual values given for the resistors. And then over here, I have 4. And I'm after n. Do you all with me? This is not something you need to calculate. I mean, it's a linear equation here. If I multiply both sides by n, I get this, right? Correct? And then I can do this a couple ways. I'll multiply both sides. Well, let's see here. Yeah, I can multiply by 99 to get rid of this thing. It doesn't really matter at this point. And now, if I want to go ahead and solve for n here, I'm going to have, what is that? So I'm going to have 100 times 25 minus 25n equal to, and this is an n here, so it's 4 times 99 times n. Take this to the other side, and I have 4 times 99 plus 25 times n is equal to 100 times 25. And that means n is equal to 100 times 25, 25,000, or 100 times 25 divided by 25 plus 4 times 99. And what is that value? Can somebody just do that for me, please?
Sure, that's the 5.9.
Yeah, and you can't have a 0.9 sample. 4.9 rounds up to 6, doesn't it, class? I mean, 5.9 rounds up to 6. Do you all with me?
Yes.
And I think that's the answer, but I don't.
That is.
Yes, we've got it.
So this is 6. Okay.
Oh, I just have a question. How did you get why did you multiply the standard deviation by the mean value of x and where that?
Read that. You're about to get it. In the problem statement, it
I
says
see that the
a
standard
var-
deviation is 2%.
2.02 is 2%.
Why did you multiply that by the mean value?
Because it says 0.2% of the mean, right?
Yes.
2%
2% of the true
2% of the
population
mean.
mean.
The mean is given
Why you square it again? Okay.
because
Okay, good.
variance. Remember, we're doing the variance of the sample, not the variance of the population. This is the variance of the sample. The variance of the population is given, which is odd, because if you got that, why are you doing this? But we're going to see later on. He's doing this to set the stage. We're going to see how we estimate all these things. And statistically speaking, it gets really interesting after the next 2 sections. All right, next one. Or is there another part to that one?
Yeah, it's just asking how large must the sample size be if the true population mean is still 100 ohms, but the true standard deviation is 2 ohms.
Okay.
So, yeah, really the only thing that's changing is the 5 ohms going to 2 ohms.
All right, so if the sample mean itself, or wait a second, standard deviation, right?
Yeah, the standard deviation changed to 2 ohms.
Goes to 2 ohms. Well, how do you do that now? Still 5 or still?
It's the same thing.
2%?
The only thing that changes is that sigma squared over n. The sigma squared becomes 4 instead of 25.
That's right. That's exactly right. But you all follow me on this? If this equation is good, sigma now is going to be, instead of 5, it's going to be 4. Instead of, sorry, 25, it's going to be 4. 2 squared. 4 over n. Might as well just do this to be sure. So we're going to take that equation. I'll put it down. The variance of x bar is equal to sigma squared over n, capital N minus 1 over, n, pardon me, over n minus 1. And that's now equal to, that's still going to be 0.02 times 100 and squaring it, or 4 over here. But now, I just took this equation right here, and I've restated it, and I'm going to adapt it. So if the standard deviation is 2, squaring it would be 4, right? So I have 4 over n times n 100 minus n over 99 equal to 4. Can you tell me what that is?
1.
You go ahead and multiply both sides divide by 4 and multiply by n. So I get, over here I'm going to get n equals 100 minus n over 99. This is kind of an interesting one. You all with me? Right? And what is that going to be? That's about 1. It is 1, isn't it? It's close to 1. Y'all agree with that? Just by looking at it? It is 1, yeah, by definition.
Exactly 1. Yeah.
Yeah. Okay, so that's an interesting thought. That was, is there more to this?
There's part C.
Part C.
And it tells you that if the sample size is 8,
Okay, hold on. All right, so now this is part C.
and it says if the sample size is 8, what is the standard deviation of the sample mean for the population of part B?
All right, so they want this, or I'll put x because I've been using x, and they actually want this, square root of this, right? That would be equal to square root of, and here we're going to have sigma squared over n, capital N minus small n over n minus 1. The only reason I'm doing it this way, I keep rewriting these formulas so it stays with me and hopefully stays with you. All right, now they give you a small n of 8, and this is part B, so for part B, sigma is 2, right?
Yes.
And then, then we just plug it in. So here we're going to get 2 squared is 4, right? N is 8, that's 1/2. Then I get capital N, which is 100 minus 8. I'll just put it in. Over n minus 1 is still 99. So that would be the standard deviation, the square root of variance of the resistors. What is that value? It's 1/2 times what? 92 over 99. Then you got to take the square root of that. Anybody? Y'all follow me on what I'm doing here? I'm trying to go through them methodically, and hopefully I'll answer any question you have. You with me? I don't know what it is, though.
134, 4.
No, I'm asking for, I want this value. I think this one might be wrong.
Yeah, because if I plug that in, I get 0.68.
That's right. But I tell you what, if you take, yeah, I think you're right. So it's 0.68, is that right? All right, that's exactly, we're doing the right thing here.
Because
Y'all
he got half of that for the answer. He got 0.34.
a standard deviation, right? That's what he's asking for?
Standard deviation.
Now, I'm not sure how that worked. I mean, I'm just saying that that's the right answer by any. He could have forgotten something. I'm not sure.
Didn't you say use the standard deviation of the sample mean?
Use what?
The two columns, wasn't that the true standard deviation for part B? Was that different than the sample mean standard deviation?
This right here is the true standard deviation. And he's saying 2, right? So squaring that would be 4, right?
Yes.
That n is h by definition, right? If n is 8, we got 100 minus 8 there, correct? That's 92 over 99. I'm pretty sure this is right. It checks all the boxes. But I mean, he's not infallible, and there is no solutions for this. There's nothing to see if he made a mistake. Probably he made a mistake here. That's just plug and chug at this point. Are you with me? Is there another exercise? Are we done?
That's all the
All
exercises.
right, let's go to the problems in this section real quick. Because if I can do this, if I can get through these, then I can get into the actual, not variance of the sample mean, but variance of the samples. Think about this. This is the variance of the mean value. It's another function. The next thing we're going to talk about is variance of the actual samples and the statistics of that related to true variance. If you read through this section, he's got some interesting comments. Some of it is hard to handle, but so this is problems now. And this is 4-2.1 in the back. Go ahead.
All right, it says a calculator with a random number generator produces the following sequence of random numbers.
Pay attention to this. This is a good one. So go ahead. So we got from 0, 0, 0 to 0.999, right?
Yes.
Okay.
Well, it gives you like an actual sequence of random numbers.
Oh, he isn't. Oh, okay. I got the wrong one.
No, that's part B. You're doing part B.
All right. So he gives you actual values, right? Yes. All right. I'm not. Go ahead. So just assume you got some actual values here. Say x1 all the way to x6 or whatever he has, right? He asked for the mean of those, right?
The sample.
Yeah. And it goes from x1 to x9.
Or x9. This is samples, right? So the mean of this, right? That's the mean of the actual samples. It's not a statistical variable. Would be 1 over 9, the summation of xi from I equals 1 to 9. Well, that's the average value. Add them all up, divide by 9. That's it. I don't know what the answer is. Anybody want to try to add them up real quick? Go ahead. Is that right? Did you do it? What? Did you do? 0. What?
373.
Is that the answer? Does he have that answer?
It is.
By the way, I didn't give you this. Here, sorry. Here. You're usually the guy. Okay, next part.
Okay, so part B is if the calculator produces 3-digit random numbers that are uniformly distributed between 0.000 and 0.999, find the variance of the sample mean.
All right, now this one, remember, does he give us anything about the true mean? Here it is, right? That's the sample mean. Sorry, that's the sample mean, right? But in general, the variance of x would be sigma squared over n, right? Does he have anything about number of samples or anything like that? How do you get the variance of anything? Forget about what we just covered earlier. How do you get the variance of anything? We got a density function for that, right? Uniformly distributed from 0 to 1, call it, right? Here's 0, here's 1. The density function, think of it as f of x. We'll call this just x. I know it's, well, we could call it n as numbers, right? Right? It's got a height of 1. How do you get the variance of anything? Well, first, you know that we could get, if this is a function, right, and this is n is the variation, I can get the expected value of n squared, right? That's the mean squared value, correct? And if I take that and I take minus the average value of n, right, that is by definition sigma of n squared, isn't it? I'm trying to show you what he's making you do is think about the fundamentals right here. So here, I need the expected value of n squared. Well, that's really what? It's the integral. You can do it in continuous time from 0 to 1 of n squared dn, right? Correct? Because the density function here is just 1. He made it easy, right? The probability density function is 1. Take that times n squared. N is the variable. And I know n is usually an integer value, but I'm trying to just show you. It could be anywhere from 0 to 0.999, which is 1. Do you all follow me? So what's this going to be? Well, that's n squared over 3, right? Or it's really 1/3. So that's equal to the moment, right? And what is the expected value of n? Just take a look at this. What's the average value? Isn't it half?
0.5.
Right? So, and it's actually this squared, by the way. So this is going to be 1/2, right? Now, I'm going to write this down there. So you know that sigma squared is really equal to, I'm going to just call it x squared minus x bar squared. That's the one you're used to, right? We want the variance, correct, class? Just take a look at this. This is this. It's the moment, right? Mean squared value is 1/3 minus, that's 1/2 squared, 1/4. So that's really 4 minus 3 over 12, or it's 1/12, isn't it, class? Now, that had nothing to do with the theory we just talked about in that section, but is that the right answer, by the way?
He doesn't really have an answer for that one, but yeah. He literally just put that.
He has to, right?
No, he put 1 over 12. That's just like all he put.
Well, that's it. I mean, that's the answer, right?
Yeah.
1/12. Do you see it in there or not? It should be 1/12. All right, what else does he ask for?
How large should the sample size be in order to obtain a sample mean whose standard deviation is no greater than 0.01?
All right, here you pay attention now. We got the mean, right, of the samples, right? This is the equation for variance, right? With me? Now, this is for part 2. We have the actual variance, right? That's what we just got, is 1/12. They want a variance. Say that again about the variance.
This is a standard deviation no greater than 0.01.
Okay.
And how large should the sample size be?
He gives us the standard deviation is variance of, and I'm just calling it x, right? Is 0.1 or what?
0.01, like no greater than 0.01.
All right, this is an actual value. He doesn't have it times something here, right? So that's this, right? So I got to square that in order to get the variance, and that's 10 to the minus 2 squared is 10 to the minus 4th. You agree with that? Everybody follow me? That's this squared is equal to sigma squared, and what we got
1/12.
1/12 squared, sorry, divided by n, correct?
Or wouldn't it just be 1/12?
Oh, yeah, I'm sorry, 1/12. My bad. You agree with this, class? I'm sorry, it is the variance there. So that means, what is n? N is equal to 1/12 divided by 10 to the minus 4th, or times 10 to the minus 4th, and what is that going to be? I don't know. Anybody? Don't trust the book's answers all the time. Just take 1/12 and multiply it by 10,000. Anybody?
$833.33.
833.33. Is that what he has? It would be 834, actually, right? Does he have that?
That's what he did.
What?
I think he said in this one his answer was either really similar.
No, he's got 455.
For what?
For that part. Just 421, right?
Hold it.
He uses the formula assuming that it isn't replaced though.
Oh, you're right, you're right. But we're using that formula too. It's not replaced. Oh,
He uses the.
I'm sorry, I'm sorry.
N minus N.
You're right, because this is, read that problem, that part of the problem again.
How large should the sample size be in order to obtain a sample mean whose standard deviation is no greater than 0.01?
And how many does he start with though?
Like as far as the initial n,
Yeah.
like initial small n, and the problem statement at the top is 9.
No, capital N. He
Capital
doesn't
N?
give it, right?
I mean, it is from 0.00 to 0.99. So I guess you could find the number of
1,000.
1,000.
If we do that, yeah, you can do it. I was thinking this is a continuous thing, but if that's it, if it's integer values, then you got 1,000 of them. Are you with me? We'll try that here. So now he's doing destructive testing, but he says the sample is limited to 1,000, and if he does that, then you're going to get the variance of that, and I like doing it this way because that's a symbol I'm used to. There's going to be sigma squared over n, and it's times n minus small n over capital N minus 1. So here we got sigma squared as 1/12, right? 1 over 12. This is 1,000 minus n over 999, and that's the variance. Read that problem again, that section.
How large should the sample size be in order to obtain a sample mean whose standard deviation is no greater than 0.01?
All right, so this is equal to 0.01 is 10 to the minus 2, squaring is 10 to the minus 4. Do you all agree with that?
That's 1 over 12 n.
Pardon me? Oh, n, yeah, I'm sorry. My bad. Are you with me on this, class? Sorry. Okay, now this, he probably has this. But again, I'm sorry. I was thinking this is a continuous random process. It's not. So for this one, I multiply by n, and I get this. And then I'm going to have to modify things. I can multiply by 12 and times 999. You can call that 1,000 if you want. And then I get this. And what do I'm going to just modify this. So 1,000 times 10 to the 4th is going to be 1/10. So it's 1.2 n is equal to 1,000 minus n. And that means 1,000 over 2.2 is approximately the value. Now again, I roughed something. What is that?
454.8.
What did he get?
It's the answer is 455.
All right,
When you do that calculation, you get like 454.7. Just round it up.
all right. I mean, okay. So this is approximately 455. And that's the way he got it, but I'm sorry I wasn't more clear about that part. Is there another part to that one?
No, that's it. And
Alright.
you circled 4-2.4 and 4-2.5. Did you want to like skip?
Hold on.
The homework's at 4-2.5.
Yeah, 4.2.4 and 4.2.5. Hold it. No, I think I did this one and this one, right? Or did I do this one?
No, you just did this one.
No, you did 421 and 425. That's what
Those are the
slide
ones
says.
assigned.
Yeah. All right, 4.2-2, 4-2.2, and 4-2.3, I think are simulations in the solution. Yeah, forget that. So I didn't assign 4.2.4. I'll tell you what, let's do 4.4-2.5. I want to do that one. I'm trying to cover these things. Before I get into the next section of theory, because some of this stuff starts getting kind of blurred as far as, variance of the sample mean, for starters, is kind of an odd concept. If they give you the sample mean and they give you the true variance, then why are we doing this? Is a logical question. You'll see later why, but it has to do with really how close you're going to be to these values. Then we take the entire variance as a statistical. I mean, we talk about the density function for it. Go ahead.
All right, so 4-2.5, you have a class of 50 students. And then the result of a particular examination is a true mean of 70 and a true variance of 12.
Sigma squared equal 12. Go ahead.
And then it is desired to estimate the mean by sampling without replacement, a subset of the scores.
Hold it. All right, go ahead. All right, and this is without replacement, so let me just put the formula up first. So it's sigma squared over n times n minus small n over capital N minus 1. Go ahead.
Okay. And then find the standard deviation of the sample mean if only 10 scores are used.
Okay. So really what he's talking about is this, square root of this, because that would be standard deviation of the sample mean. This is the variance of the sample mean. With me? So here, come over here, and now we're going to say small n equals 10, right? I think you'll see this kind of, it's going to become more and more obvious. So here I'm just going to plug it in. We got, this is 12, so we have the square root of 12. Small n is 10. Capital N is 50. Minus 10 over 50 minus 1, or 49. And that should be the answer, and that's part A. So can you tell me what that is? Just do the calculation. I didn't check his answer in this one.
You got 0.98.
Did you actually run the numbers? Or did you just look it up?
I mean, I can look it up.
I ran the numbers, I got 0.989.
All right, 0.989. Okay. So that's the variance of the mean, right? Go ahead.
And then for part B, it says how large should the sample size be for the standard deviation of the sample mean to be 1 percentage point.
All right, so standard deviation of the sample mean. All right, I'm going to go again, and I'm going to put the equation up. So this is sigma squared over n, and this is going to be n minus small n over n minus 1. I always like doing it that way. It stays with me the more times I write it. Okay, now you said standard deviation, right? So I'm going to take square root of that. That's standard deviation. Is equal to what?
To be 1% of the sample mean. Well, it says for the standard deviation of the sample mean to be 1 percentage point. So out of 100.
Okay, so out of 100, wait. No. We have 50, right?
Yes,
So
it's still a class size of 50, and it's asking for like the sample size that we need to produce a standard deviation of the sample mean to be 1 percentage point.
Of the sample, of that.
I honestly don't know. It's
Yeah,
it's
I
worded
mean, it's
kinda
got to be
strangely.
0.1. I mean, 0.0. Really, it's 1 over 100 times 50, or 1/2. Do y'all follow me on that, class? He's saying it's 1% of the mean, right?
Well, he puts in
True
parentheses out of 100. Like, is that the score? Like,
Say that again.
because he says standard deviation of the sample mean to be 1 percentage point, but then he says out of 100. So is he talking about the score of the
We'll
test?
put 50 over. He's talking about 1% of that,
Okay,
of the mean value, right?
I hope so.
That's not what it looks like in the solution.
What is it?
Looks like he wants the standard deviation to be 1, just 1. That's in like 1 point.
Yeah, like 1 point out because it's a test score. So if a test can go from 0 to 100,
Oh. He wants this to be just 1% of the possible, which is 1. You're right. Could you read that one more time?
yes.
I'm
All right. So part B, it says how large should the sample size be for the standard deviation of the sample mean to be 1 percentage point?
That is 1. You're at, because this is the square root of that is the standard deviation. All right. The possible values are up to 100, right? 1% of that is going to be 1. Okay. I'm not sure what it comes out to, but let's see. I'll square both sides, so then I have sigma squared over n, capital N minus small n over capital N minus 1 equal 1. And then, all right, what do we get? We got n equal to sigma squared times n is 50 minus n over 49. And let's see, so I get 49 is equal to sigma squared times 50 minus n, and what is that going to be? That's going to be 49 plus sigma squared times, wait a second, times n is equal to 50 times sigma squared. So n is equal to 50 sigma squared over 49 plus sigma squared. What is that?
I got 9.8. So
What is it?
10.
Does he have 10?
Yeah.
Okay. All right. That's that part. What's the next part?
How large should the sample size be for the standard deviation of the sample mean to be 1% of the true mean? And the true mean was 70. So 1% of 70.
0.7, right? All right, we can use this one, right? So everything is the same except this is 0.7. Do you agree with that, class? All right, I'm about out of time. I think you can follow me on the next step. Square both sides, right? And just rearrange it. Can somebody do that real quick, see if you get the same answer?
I got 12.9, so 13.
For n?
You square 0.7.
Yeah, you got to square this.
Oh, you do?
And get
All right.
rid of this.
It's 17.
You got to get this now. You got to get that, right? That's what he has, I bet. I didn't look at the solutions for this one, but
Yeah, 17.
is it 17?
It's like 16 point, but round up 17.
70. Okay. All right. I'm going to tell you where I'm going with this. The next section in the book is section 4-3, and it is about the standard deviation. Now, the variance of the actual sample. Do you all see that in there?
Sampling through.
All right, this is more, now he's going to have a symbol, the estimated value of the variance. Now, I'm going to have to go through this one with you because a lot of this stuff gets a little weird. And the logical question I had when I started doing this stuff, I mean, from last time I taught this, and even now, if you have the actual mean in the actual variance, why are we doing this? And I mean, it's dumb, but here's what happens. He's going to build a case showing the relationships, and he's going to say, therefore, regardless of what the samples, the actual mean is and the actual variance, we're going to be able to say from a subset, assuming that there's a large number in the actuals, we can say what the actual probability is of that variance or the mean being within 10% or 20% or 99% of some values, all right? We're going to see this, and it's exact. But he's got to do it this way to build the case. Please read section 4-3. I'm just asking you out of the decency of your heart, and I'm going to give you some problems. You're going to see, I mean, obviously, I didn't get through the theory on this one. I just did it. I'm going to go through the problems for that section, and then I got to go through 2 or 3 other things, but we're very close to finishing up. And I do some out of chapter 6, and I talk about wide sense stationary signals and some of the other concepts. They're a little more abstract, but they're useful.